Okay, I think we've reached just about the halfway point in this lecture series. The first half of the series was devoted to explaining and understanding the origin and evolution of this scientific paradigm, this false scientific paradigm, and then explaining and understanding the origin of a new alternative paradigm, which is true. Uh, and so now we reach and we can quite obviously see that this one's false and this one's true. So let's get rid of the bad one and start trying to figure out how to use the good one. So that begs the question: what do we do with these paradigms? Well, we use them. We use them to know things and to think things and to say things that are logical about nature. Okay, that's what they're for. So they create ideas, they create language, they create communication. Okay. Well, the most common use of a scientific paradigm is to teach. And that's what most professional scientists in the world today are hired to do. They're hired to teach. So, if you're teaching eighth grade science class and you introduce the genetic code, then you're a professional teaching the genetic code and you're using your paradigm to do that. Okay, so I think it's important that these professionals understand what they're doing and what they're saying. Now, when I try and discuss this with, the higher up I go in the chain of professional scientists, the more upset they get, and they start saying things to me about me that are just, well, childish. They say that I'm childish. They call me names. They say that I'm stupid and crazy. They say I'm a crank. They say that I'm an anti-science guy. I'm a flat earther. You name it. And they say that I'm a heretic. But a heretic is a good thing, and I think it's true. So I don't think that that's calling names. So then I turn around. Of course, what do you want me to do? I mean, you call me these names. I'm going to turn around and call you the names. So then I say, well, here's one that fits you. It's a submoronic, ignorant monkey boy. I think that's a good name. That describes you pretty well. Okay. Was that being childish? Yes, it's being very childish. But you started it. Okay. Don't be calling me names and then expect me not to turn around and call you names. Okay. And I think where this problem arises is because this is a childish paradigm. Okay. This is childish. To insist on using this paradigm, to believe this paradigm, that's childish. Now, this is a childlike paradigm. Okay, and there's a big difference. This is childlike, this is childish. Okay, now, Einstein said that if you have a theory and you can't explain it to a child, then you don't really understand it. Now, he believed this because he believed in his childlike qualities. He would frequently hearken back to his childhood and how he thought, and he would employ that same kind of process to the adult stuff that he did. And so, being childlike means to be curious and open and exploratory and inventive, okay? So this is a childlike paradigm and this is a childish paradigm. The primary use of a paradigm is to teach. So the most important teaching that we do of our paradigm is to the children. Okay, well, if you're teaching this toxic garbage to children, then you are damaging them. This is child abuse. Okay, we already know that it's wrong. We know that the things that we're saying are false. So we need to stop saying them. Well, that leaves a vacuum, a void. Um, how should we teach this to the children? I haven't really given that much thought. But since by default I'm the world's leading expert on the genetic code, then maybe I should take a crack at teaching it to children, which is kind of scary because a I've never taught anything. I mean, I don't. I've never been hired to teach anything. And B, who wants me around their children? I mean, this is nuts. But I'll give it a shot because hey, that's my burden in life, I guess. So if I were going to teach a group of children, let's say 14-year-olds, let's just imagine that we get 10 or 20 of them together and they bring me in to teach them the genetic code. Uh, how would I do it? Well, it depends. I mean, if you're going to give me 5 minutes or 10 minutes or 15 minutes, I would imagine that it's probably going to take about 10 or 15 minutes. And that's just to get the story to them. You know, you're not going to teach them the details. You're just going to teach them the story. It's just to get them started so that they can start being childlike and exploring. Okay. I think that you're going to need some props. I think the basic props that you're going to need is you're going to need this double helix. You're going to need this code, and you're going to need this codon table at the very minimum. So, but you're probably going to need more props too as you go along. But I'm just going to give it a shot. This is how I would teach a class of kids the genetic code, assuming that it's a science class and that these kids are going to be scientists or want to be scientists. So it's not just like you're just going to take random kids. You're going to take kids who are interested in exploring the natural world, and you're going to try and introduce them to this genetic code. So I would say, well, okay, hey, good morning. Hey, thanks for inviting me here to explain the genetic code to you. I'm going to just start by saying that the genetic code is the most important thing in science. It is, it's obvious because the genetic code is the thing that built me and you. And I am a scientist and you are a scientist, and now we're discussing science. So without something that builds us, then science itself can't be built. So that automatically puts it in the middle of science, makes it the most important thing. And it's the most interesting thing. Okay? You'll never, if you become a scientist, you'll never find anything in science that's more interesting than the genetic code. And it's the coolest damn thing you'll ever see. I mean, if you're into stuff like video games and, you know, TikTok and stuff like that, this is much cooler than that. It's kind of like that, but it's cooler. It's the most complex code on Earth. And that just stands to reason because life is the most complex thing on Earth. So it must be based on a code that is equally complex. It's the most complex thing. And it's complex because it's non-linear, which means that there are many variables, many logics, many associations. It's horribly non-linear. You know, unlike if-then kind of linear logic. This is more of a cloud type logic. Okay, very non-linear, very complex. But because it's so complex, life has miraculously made it small. It's compressed it down. We can look at it in small things. We can find this big code in the smallest things. Okay, it's the biggest code in the universe. This is the code that created life. Okay, this is the origin of life. Okay, you're going to find this code wherever you find life. Okay, there's life. The universe is just teeming with life. Okay. We just haven't found it yet. But when we do find it, we know logically that we'll find this code. This code is so complex and so powerful, we can actually hold it in our hands. This is the genetic code. This is how the universe generates life. Okay. Well, how cool is that? That's the coolest damn thing in the world. Now, this is just a simple machine. Okay. So obviously, you know, life is a complex machine, but life and this simple machine share the same logic. They share the same machine language. So this is a code that operates before there's any life. This is the origin of life. So in order to understand this, we have to understand science. So science is a process of understanding nature. We understand the logic of nature. Okay, in order to understand the logic, we have to gather facts. Well, we gather these facts, and then we come back and we think about them, we talk about them, and then we have to use our imaginations. Because some questions are so big that we can't know all of the specifics. So that's when we need to generate a story that's consistent with those facts. So we have to use our imaginations. We have to imagine the story. Okay, so that's what science is. It's this awesome process of imagining how nature works, and then we go out and we find these facts, and then we put them all together. Well, there's nothing that's bigger than life. There's nothing that's more important. And so what we have to do is we have to blow our minds to imagine the biggest possible story. So in the case of life, we know that it's a logical process of the universe. So we have to start with the universe. Well, the universe is 15 billion years old. So we go back 15 billion years. Was life there? Yes, life was there. Then the universe starts making these atoms. Okay. And it takes, I don't know, billions of years, but it takes 10 billion years before it makes the atoms of Earth. Okay. So then we have about 5 billion years ago. I'm using round numbers. Okay. About 5 billion years ago, the Earth forms. Was life on the Earth? Yes. Because life is a logical function of the universe, like gravity. Gravity brings the atoms. Quantum mechanics creates the atoms. Gravity brings the atoms. Life arranges the atoms. So it has a code that does this. So it had to start working on this code 5 billion years ago, and it's still working on it. So there's a code that takes these atoms on Earth that are moving around seemingly random, and it learns. Okay? It's just like an artificial intelligence. It's a machine. It does machine learning. It's a computer. But more importantly, it's a crystal. So we can take a crystal. This is a crystal. This is a simple crystal. It's called salt. Okay, it's halide. It's sodium and chloride. So the Earth put this crystal together using a computer code that is simple. It looks like this. Okay. Now the difference is that these atoms, they come together and they freeze up in this rock. Well, the life atoms, they never freeze up. Okay, it's more like a liquid. It comes out of the ocean. It's a liquid crystal. This crystal has to keep moving. Okay, so it needs a crystal code that can keep it moving. So it does use the same thing as salt, but then it uses something else called a dodecahedron. So now the code is the animation between crystal codes. It takes the logic of the universe, the symmetry, the spatial symmetry of the universe, and it animates this information. And that's what this machine does. It's animating spatial information. And that's how it serves as the code of all life to start getting life to be made. So the way that we can think about this is as a computer. Okay, it has a central processor, which is the code. Okay, it has a hard drive, which is the storage. And then it has like a screen so you can watch the animation of life. So we can think of all the atoms on the Earth as the screen, and we can watch this screen evolve. Eventually, this crystal that I'm a piece of that crystal. I'm like one piece of that crystal. You're a piece of that crystal. We interact in time and space, and we might, create families and create new crystals, and it just goes on and on and on. And we interact with the other crystals like cats and dogs and horses and elephants, and we interact with the smaller ones too, like amoeba and sponges and bacteria and viruses. And all of this is one single screen that's animated. All of these different pieces are interacting in this nonlinear pageant of life. Okay, but it gets way cooler than that, because when you come to the individual like me or you started out as a single cell. I start out as a single cell. Okay, that cell is a computer. It's a machine. The information is in the machine. The machinery is in the machine. The code is in the machine. My genetic code is in that first cell. Okay, it's almost like your genetic code. It's just they're slightly different. Now this code is used to create a second cell. Okay, now this new thing, We started with one cell and we create two cells. And this new thing is a new code. The code of one cell is different from the code of two cells. So now it creates four cells. So now through time, we're actually generating these new codes. 4 becomes 8, 8 becomes 16, 16 becomes 32. At each level of this process, what we're doing is we're creating more cells. Well, they're keeping, they're each sharing the original instructions and the information, but now collectively they're generating more. So what we do is we start with a robot, a single cell. We're creating a fleet of robots, a colony of robots that interact dynamically through time. So now this self-generating process is creating 37 trillion of these cells. Well, now all 37 trillion are a new thing. It's one thing. It's you. It's me. Okay, now your 37 trillion interact with my 37. So we start over. Now, where we start out with cells becoming colonies of cells, now we get people becoming colonies of people. Well, this pattern repeats itself all the way down to the atoms and the molecules. And we know this is true because science has proven it. They have gone out, they've done these great experiments. They show that these molecules are doing exactly that. Okay? And we can see that. We can see that this is the hard drive. This is the CPU, and this is like the screen generator. This generates the screen. This is what we call a codon table. What this is a data table. They went out and did these experiments. They did this data. They call it a codon table. It's called a codon table because it has 20 codons on it. Okay, these codons are variables. Okay, we derive the variables from the code. We get 20 codons off of this. Then we instantiate, or we assign values to those variables, and those variables are complex. Okay, but the values are complex too. What they are is they're molecules. So there's a molecule. This is one of the protein molecules. This is one of the DNA molecules. So there's four of these, four different ones that are letters, A, C, T, and G. Okay, they create this structure. All right, this code generated this structure. These molecules evolved to make this structure. This code generates this table. These molecules evolved to do this table. This table, you can take the molecules out of this table and operate this machine. The data from these experiments is the machine language for the machine. This machine is an emulation of the code. Okay, it's not the code. It's a machine emulator of the actual code. Now the computer itself is not like the computer that's on your desk. It's not a Turing machine. Okay, it's a von Neumann machine where there's a network of information that gets processed one click after another. Okay, but that's what makes it so complex. That's what gives us this level of complexity. So now what we can see this ball as, this is the damnedest thing you'll ever see. This is a crystal ball. Okay, this is like the brain of life. It actually is so smart. There's so much intelligence represented in this ball. It makes these fabulous predictions. So it'll predict that if you see, let's say, 3 of these somewhere, then at some future point you'll see 1 of these. So it's predicting these unpredictable events. It's absolutely bizarre. When you see what these molecules are doing, it's miraculous. I mean, it's miraculous that you could take all of the molecules, all the atoms on Earth, and all of a sudden, 5 billion years later, you got us. It took the Earth 5 billion years to create you. It created you at one cell, and then 14 years later, you're these 37 trillion cells. Well, that's a miracle. That's just a damn miracle. But it's doing these miracles at every level. It did the miracles at the lowest level. It's doing the miracles. It's still doing them. You and I are still following this code. It's called natural selection. That's how life works. Life uses natural selection to create us. We use artificial selection. So we talk about selecting dogs for breeding. Well, that's how we understand natural selection. But artificial intelligence is the same thing. Natural selection is the genetic algorithm that creates intelligence. So artificial intelligence teaches us natural intelligence. So in the same way that molecules become a brain and smart, you and I become a brain and smart. So we see this beautiful symmetry throughout life. Life is this unbelievable miracle machine that's building a single complex crystal over the surface of the earth. Now, I don't understand this, and I don't expect you to understand this, but I expect you to recognize how cool this is and realize that if you're going to be a scientist, and if you want to study this, you're going to spend your entire life trying to figure it out because it's so damn complex. It's so cool. So if you were to do this for a living, if somebody actually was dumb enough to hire you and pay you to go into the office to play these games, this is what you would be doing. You would be learning the code of all life. You would be asking questions like, how does this work? How does this work? What does this mean? What does this do? Okay. How do we build a toy that shows how it works? Okay. So that would be pretty cool. I mean, you would be a pretty cool dude if you could get paid. If you get somebody to pay you to do that, that would be pretty cool. I can't get anybody to pay me to do it, but that's okay because I have a job. Anyway, are there any questions?